So, classes. What do people think about classes? Nice. Up, down. Just how about just thumbs up, thumbs down?
Wait, what type of classes?
Generic.
Wait, classes as an object, or classes as in I learned?
Like this class. This class. Thumbs up, thumbs down. No, I'm just thinking. I'm making a joke. Okay. Yeah, the Python programming classes. Okay. What do you guys? Let's let's go around. What is the tricky thing that? Give me a couple words of things that you're having trouble with. Conceptual. What would you say is the? What would you say is? Are you having? Is your feeling about classes and objects?
Fully comprehend the init.
The init. Okay, that's good.
That's like one of my problems too, but also I get confused as to what to put in the parameters sometimes, because sometimes it's like self-dot, and sometimes it's like, you use the gravitational wave thing or whatever.
Right.
So just like a formatting.
Right. Okay. Okay, let's see here. I wish I could sit over here, but actually maybe what I'll do is I'll come onto this side so I can more easily look to see what you guys are seeing too. Okay. All right. So let's just start by making a class. Foo. Inherit from object. And okay. This is simply a class. Okay, and it's only got one attribute, which is this data thing. Okay, but I can't really do anything with foo right now because it's just a class definition. It's like it's sort of, like a function definition. You define a function, but you have to call the function in order for anything to happen. But if I just do foo, there's not really anything happening. So with a class, what you have to do, a function, the one thing that's different from a function is that a function, you can call a function and get output. You don't have to do anything else with the function. With a class, in order to do anything with the class, you have to instantiate it. And that's what the analogy in the Yesla car thing was the difference between the blueprint of the car and the actual car, right? So the class definition is like the blueprint, but you can't drive the blueprint, right? You have to actually make the car. So to make the car, you do something like this. So this is how you instantiate a class. Is you say the name of the class, so foo, and remember the capitalization matters, so capital foo, and then parens. And it's sort of like you're calling a function, right? It looks sort of like you're calling a function. But now F is like the car. Foo is the blueprint. Foo with parentheses, that's like making the car from the blueprint. So now we have F, and now we can do stuff with F. So foo, let's do this. That still works.
Yeah, why does that work?
Because the class definition is itself a thing, but yeah. So a better maybe.
What happens if you try to modify something in there? Like try to say
if
foo.data
if you did this, for instance,
Yeah.
um,
That works. Wow. That is really weird. So apparently, what? So you change
Yeah.
the class, it changes those objects too?
yeah.
Wow. That is cool. I wonder what happens
Yeah, that's a
if
little
you
bit weird. I wasn't expecting
I
that,
wonder what
honestly.
happens if you set f dot data to 14 and foo dot data to 13.
Yeah, no, that, so this certainly, so, that's 14.
Foo dot data is 13.
That's going to be 13.
That's really interesting.
Yeah, maybe that was only confusing and not helpful. Okay.
Makes sense to me.
So one other thing they showed in the class that came up, so when we say creating instances,
Mhm.
that's the idea of as
Right.
So
Yeah.
creating instances means
Right. So here. Let's try to make this a little bit more informative. So this right here, this is the creation of an instance of the class foo. F is an instance of the class foo. So it's F is an object. Now, what happens when you want to create a class is you do this. Okay. Yes. Yes. Object is the parent class. It's the parent of all classes. Yeah, it's the superclass. Okay. So, okay. So the init function is when you instantiate a class, so when you do this, right, the init function is executed when you do this. And any of the arguments you give in the class instantiation are the arguments that are passed to init. So the thing is that this is a way that you can set up things in the class when you instantiate it. So if we try to do this right now, it's going to give an error. Because, remember, what you pass here gets passed to the init function. But the init function, as we've defined it, is expecting an argument, this argument init data. But we didn't give any argument here. So what it's saying is that I went to go try to execute init, because you're instantiating the class, and I went to go try to execute init, but it's missing its input, it's missing its argument init data. So now we have to, the way we fix that is we give it an argument that would go into the init data. So let's give it something like this. Okay, so now it worked, right? So what is foo.data now? F.data, sorry, F.data.
That would be 51.
Right. Because we gave 51 as an argument to the class when we instantiated it. That got turned into the argument to the init function. And what that function did was take that argument and set it to be self.data. Right? So data started out being 12 in the class definition, but then when we instantiate it, that actually changed that data. This is kind of the point of, see, it didn't, foo.data is still 13. Now f.data I just changed to be 14, so that's going to that's like updating it. Yeah, okay. So does anybody have questions about this, about the class instantiation here? Does this answer your guys' question about the init? It's okay it's okay if it doesn't. I mean, you feel free to, keep hounding me. Say, no, Jamie, you're not explaining it well. You can throw things at me. Okay. Yeah.
So in class we had different methods in class. So for this specific method we have init.
Mm-hmm.
For others we don't. What is the difference between having init and not having init?
Right. So you don't have to have an init. The init method is there to allow you to pass parameters to the class when you make it. That's the point of the here. Let's take another example. Let's take this part out. So we only have this, okay? Now, this foo. Okay, right now the foo definition doesn't come with any attribute called data, right? I didn't define in this class definition something called foo.data. The init function, however, will create an attribute called foo.data, but it's not there initially. So the data attribute will only exist once the init function is called, right? If the init function is never called, then that attribute won't ever be there. So that's why right now when I do foo.data, capital Foo, there's no data attribute. However, if I do this, right? So when I instantiated the class, I gave it this number, 12321, and that was passed to the init function, which then said, okay, when I initialize the class, I'm going to create an attribute called data, and I'm going to assign that input argument to be what goes into that attribute. Does that make sense? Again, the point being that the init allows you to do some setup, some initial setup. Be good to have some other examples, but so I could, okay. So what I did here was I created another method for my class that is going to print self.data. So I've got this class that wants to do something with this data here. If I comment this out so that I don't do anything with that init. Oops. Oh yeah, we can't just comment that out. We have to do that. So, okay. So in this case, I instantiated the class, and I passed it an input argument. But the init didn't do anything with that input argument. It didn't create a data attribute, right? And so then when I try to access it, there's nothing there. And if I were to try to execute this method, it gives me the same thing. There's no attribute called data. So I could set it and now I can do something with it. So I guess the point I'm trying to make here is that if you've got a class that wants to do something with data, like let's just say, I want to have a class that does this. I want to have a class that prints out the value, that does something with self.data. So I can do this. Oh no. Sorry, I've got to do this first. This. And then, test can't do anything. Okay, well, let me set data, and then I can run self.test and have it print out data. But it's easier if I just, when I instantiate the class, I just can instantiate the data that I want. And then I can just say, and then, it's basically like a shorthand to a short way to get data into your class when you instantiate it, rather than having to do it after you instantiate it. Does that make sense? Mm-hmm.
Whichever argument or parameters you want to enter to your class goes to init.
Yes. I mean, you can. So, like I showed before. I mean, you can. It doesn't have to go in init. You could initialize, then set the data, then do something with the data.
Yeah, you definitely do not have to use it in it, but as you just showed us, it is quicker
Right.
to just have it there. Because the examples we are doing right now in notebooks, the localization,
Right.
so we did the init, we set it, then now we are just giving the arguments to the instances to the
Right.
So it really helps us to init in the localization in the beginning to
Right.
all those arguments.
Right.
So each different instance.
Right. So this is a way, this is an example of doing that. So I'm calling the same thing. I'm making another instance of the class foo, but I'm giving it different input parameters. So it's the same. These F and G are the same class, but they're different instances of that class with different data inside of them. Would be better. I wish. Well, we have the. I mean, you guys have worked through the workbook with the gravitational wave detector thing, and in that case, you give, when you instantiate the class, you give the location, right? The latitude and longitude. Right. Right, with the different locations. Right. Is there any what other thoughts do you guys have about classes? Any other questions or confusions? Yes. Yeah. So is this?
Last week when we did the plot part, it was basically creating tuples and then just print like X,
Right.
So it was pretty simple. You just put a plot and
Right.
but this is like more.
So are you talking about from the capstone?
Yeah. Well, no. Notebook problem number 6.
Uh-huh.
So after we set up all of our classes and all of our instances, it says now plot them. So that's where like the whole little text is confused.
Right.
Or if you could show an example about it, or like the whole different example.
Okay. Hold on. Over here. So, in here?
Yeah.
Which, this part?
The get detector versus time.
Oh, okay.
Yeah.
Okay. Here, let's, okay.
But I think to be able to do this, we would have to have all the things first.
Right. You're saying we have to have executed the, right.
Not really. This code is not done at all, so we would have to code everything to get that.
Oh,
Like we would have to do all the exercises to be able to.
oh, I see.
But if you can show an example.
No, but this, oh.
You know, like, yeah.
Yeah, is there, I don't have that. How can we,
It's always
yeah, yeah.
Is there any specific question you have?
Oh, you could show like an example about a plot.
Okay. Let's try this. So, okay. Okay. Import matplotlib as. Let me remind myself how you guys were. Oh, you do PyLab. Okay. So, okay. NumPy is a way to deal with arrays of numbers, right? Like lists of numbers. I think you guys already did that. So, this is a function which gives me, so arange gives me an array, an array with 100 numbers in it that just go from 0 to 100, 0 to 99. Okay. So let's assign this to x. All right. Let's say that y equals x squared. You know this notation, right? The star star? Okay. So now, I probably want to do, don't you guys have that magic, where's the magic? Oh, well. So basically, I mean, you guys have done, yeah, maybe you haven't. Okay. Okay. So usually when you're plotting, you guys have you guys done plots in like math class? How have you done plots in math class? Have you drawn them by hand? You have? That's what we did when I was in high school. We like drew things by hand. I thought you guys were all like iPads and stuff now. No? Okay. So you've drawn the plots by hand, right? And so what did you do? You said, here's the first pair of x, y, right? I go over to x, and then I go up to y, and I draw a little mark, right? And then you go to the next point, which is the next x, and you go draw the next y point, right? So in Matplotlib, what it does is it says, here are all the x points, and here are all the y points. And those two arrays, so the x array, this array is 100 points, right? Because I said when I created it, give me an array with 100 points in it that just go from 0 to 99. And then this is also 100 points, because I said just take that array with 100 points in it and square every element and give me a new array. And that's going to have the same number of elements, right? So now when you give when you give x and y to the plot, it knows, right, what you're saying is here are all the x points and here are all the y points. And it's basically knows that the first x point goes with the first y point, the second x point goes with the second y point, and so on and so forth. So instead of giving it a whole bunch of xy pairs, I just give it the whole x array and the whole y array, and since those arrays are the same length, it just matches them all up, right? And then all it does is it does basically exactly the same thing that you do on the graph paper. It says, okay, I'm going to go to point 0, which is the first thing in the x array, and what's the first thing in the y array? That's 0 squared, which is 0, right? And it goes and it draws a line. And then it goes to the next point, draws a point, goes up to 20, and says, okay, what's 20 squared? Well, that's, 400 or whatever it is. And then, just goes on and draws all the points. And then eventually gives you the full graph. That's really all that the plotting is doing. I mean, there's a lot of fancier stuff you can do, but the basic thing is you take the x array and you take the y array and you give it to the plot and it makes it. So it's a little bit different than you might have done it when you draw it by hand, because when you do it by hand, you probably are thinking of one x and one y that go together, right? And then the next x and the next y that go together. Does that make sense? Just trying to think of how you guys might have done it in your math class. But in computing, this is the standard way to do it. You give all the x's together and all the y's together, and then the thing that does the plotting just matches them up to make the points.
Well, I understand that part, but if you go to notebook problem number 6,
Mm-hmm.
so on notebook problem number 5, we're basically supposed to copy and paste the data with the red marks. And if you see up there, it says plot. If you go down on 6, it says plot get detector time. And if you go up,
Mm-hmm.
it's not like an X, Y. Like if you go for the function, a little bit down, get detector time is just that. So what are we supposed to plot with?
Right. Okay. Right. So I wish we had the actual notebook to work with. So get detector time is a method of the class, right? And what get detector time does is that it returns you an array with each element of the array is a time step, okay? So it's very similar to that arange function I just called, right? Because that arange function returns a array that goes 0, 1, 2, 3, 4, 5, 6, 7, 8. Like, you can think of those as seconds, right? So what you'll do is something like this. You'll have your let's call it H1 detector equals, what is it called? It's something like gravitational wave detector, something like that, with latitude, longitude. Okay? And then what you do to call that method, you say h1.get, what is it called? Get detector time. Get detector time, right? This is how you call the method, right? It's just like you calling a function, but you're calling a method. So this is going to return an array. So what do we do if we want to plot it? Well, we say, you know what? This is going to be x. Right. And then what is the y going to be? Well, it says, I want to plot exactly to plot it against get detector noise. Right. So you would do h1 dot get detector noise into the plot function.
Yeah.
You could. This is a little bit. This is clearer. I would do it this way because it makes it very clear. Remember what I was saying is that the programs are for humans to read, not for computers to read. So it's easier for a human to read this and say, oh, okay, this is what x is, this is what y is, and then you do pylab.plot x comma y. Yeah, that's like. Yeah, right. I mean, you can do that, and it's, you know, sometimes it's nice to be more concise, but I think it's. I mean, sometimes there's benefit to being more concise, also in terms of computational stuff. But usually it's better. I encourage you, especially at the beginning, to be more verbose. This is more verbose. It's being more explicit about what you're doing, right? It's saying, I am setting x to be this. I am setting y to be this. Now I'm going to plot x versus y. So does that make sense? Yeah. Yeah. So the point is that these functions give you an array. And it just so happens that these two arrays are going to be the same size, because your class is defined such that the time array and the noise array will always be the same size. So that's part of the class definition that enforces that. Sure. Any other questions? Was there any other part of the workbook that people were thought was tricky? No other questions about classes or? Mm-hmm.
So, in the code example we have here, it's the start.
Right.
And we have it because.
Right. So yeah, you had asked about the confusing part of the self. Yeah, the self is just kind of a confusing thing in Python. And it's just one of these things you kind of have to get used to. It's a little bit hard to explain. But self refers to the object itself. That's really the most succinct way to say it. So when that self thing it has to be there in the definition of the class method, but it's not there when you call it. And I can't give you anything to say about that other than that's just how it is and you have to remember it. You'll once you do this for a while, you won't think about it anymore. But for now, there's no good like rhyme or there's no good explanation I can give you about that other than it just has to be the self thing. It has to be here in the definition, and then it's not here when you call the function.
Here's my reasoning.
Mm-hmm.
Because Python just sends some data that's for self every time. So if you have anything else, then you...
Yeah, no, that's true. I mean, what's kind of happening...
Technically name self whatever you want it to.
You can, but don't do that. That would be super confusing because everybody calls it self. Like this, it could be named anything else, but everybody calls it self, and it would be confusing to people if you named it something else. I mean, technically, what's happening is that when you call a class method this way, the G, this thing, is being put into self. It's like this. It's in some sense, it's basically the equivalent of saying that G.test is the equivalent of test G. It's sort of like that. Okay? And so this is a little, when you write it like this, it makes a little bit more sense in some sense because that self argument, right? Well, that's G. That's the thing itself. So that's how you can then modify the data attribute of that thing because that's been passed into the function. It's just confusing. I know, I sympathize. But there's nothing I can do about it other than to sympathize with you. But you just have to remember that it has to be there in the definition, but you don't do anything with it when you call it. You just jump over it to the next one.
So whenever you are creating your class and you are defining your methods,
right.
You put set.
Right.
Maybe just think of as syntax, specific that.
Right. Right. Yeah, the two places where self matters is that one, it has to be there as the first argument of your methods. Two, and this is much more important, is that self is where you store all of your attributes of your class, right? Self.data. That's where, remember, this is different than this, right? Those two lines are different. One sets the second one sets a variable named data in the function to be the value of init data. The first one sets a attribute of the class called data to be the value of init data, right? The first one is persistent. The second one is not. The first one will remain there after that function is executed and completed. The second one will not. The second one will disappear. And this is really, in some sense, this is what I was saying back at the beginning of the week. This is like the whole point of classes, that you can do this, that you can set self.data, and that exists after you've done with the function. This is really, I can't emphasize this enough. This is the real takeaway. This should be the real takeaway of classes, is that thing right there, the distinction between these two lines of code. This is really the whole point of classes. So I really want to make sure everybody understands that point. Everybody gets that, right? I mean, we can make this explicit here, right? What's going to happen? What do people think is going to happen here? So I'm going to execute. I just instantiated the class with this input parameter 33333. So 33333 goes into init data. Init data gets assigned to self.data and to data. That's all I did. That's all I did when I initialized the class. Now I want to execute the method test, right? So test doesn't have any input arguments because remember you ignore self when you're going to call the function. It has to be there when you define it, but then when I go to call it, I leave it out. So I'm going to call f.test, and what's going to happen? It's going to print, first it's going to print self.data. So what's the first thing it's going to print? Given that I initialized the class with this. It's going to print 33333, right? And then what's it going to try to do? It's going to try to print data. But what's funny about that? Data is undefined in this function, right? In the namespace of the function test, there is nothing called data. There's self.data, but there's nothing called data, right? It's going to be an error. I printed out 3333. That's what self.data is, because self.data was made in the init. But then data, that was also made in the init. But it went away after the init function was done. The init function finished executing up here, right? At here, by this point, the init function was completely done executing. And then that data, the just plain data, completely went away. So then test says, okay, I know what self.data is, and then when I go to get print data, there's no variable called data anymore. So this really is the whole point of classes, because self, in using that self thing, you can store whatever you want for later usage. Try to think of other good examples of the what? Yeah. Let me. I guess they don't. You guys don't necessarily always get through the capstones, right? That's just kind of like extra stuff.
No, I mean, some of them, they do.
Right.
So far, like, we have seen the definition.
Right. Yeah, this capstone. Let me just.
It's all going to be such like one in which I'm doing a little report on it.
Yeah. Let me just talk about this this week's capstone. Just a little bit, just to kind of give you guys. Let me just walk through it, just so you. Yeah. Break it down. Exactly.
I looked at it, just looked at it.
What?
I looked at it, I'm like,
Yeah, it looks complicated. It is a little bit complicated. But I was trying to. So what I was trying to do with this capstone is actually take some real LIGO data so you can see what happens. This is really very similar to what we do to actually detect the LIGO events. So, okay. So this is standard stuff. Import the libraries we need. Okay. So what are we going to do here? I'm going to make something called a filter. I'm going to make a class called a filter. And a filter is, okay, remember when I played those sound clips earlier? There was the one that had all that high-pitched stuff in it, and then there was the second one I played, which was like the low rumbling noise. The difference between those two sound clips is that the second one had been filtered. So filtering is the process. It's like a filter in a pool or whatever. It's like there's stuff here that I'm going to put through the filter, and then I'm going to catch it in the filter so that it doesn't go through to the next part, right? So that's what happens. We made filters that took out all the high-frequency, high-pitched lines, and then the second data had all the high-pitched stuff removed. So that's what a filter does, and it basically transforms the data in some way. So that's why this has this method called filter data, because the whole point of this filter object is going to be take some data, and then the fs is the rate at which the data has been sampled, and then filter it in some way. Mm-hmm.
Shouldn't that definition of the main one just return the data back since it's just a blank filter that doesn't give it?
It could. I mean, it could. Yeah, that would probably be a better way to define it. Actually, to have it do return data. Yeah, that's probably better. Okay. Then what we do here.
A whitening filter sounds like it's in your adds white noise.
No. A whitening filter does something kind of funny, is that it takes a sound that has features in it, that has like sounds in it, and makes it sound like white noise. So white noise is just like a shh. A white noise means that it's like all the sounds. What is white light, right? White light is all of the frequencies, all of the colors, all at the same time, right? That's what a white light is. A white noise is the same thing. It's all the frequencies of sound all at the same time. And that actually sounds like shh. It just sounds like something like that. So that's what you call white noise. So a whitening filter is this funny thing that we use in signal processing that takes something that has sounds in it and basically turns it into white noise.
Doesn't that sound really pointless?
It does sound pointless, but it's actually super powerful. And I'll leave that as extra credit for you to go onto Wikipedia and figure out. So I won't get into the details of why we need to do that. But the point is that, so look what I'm doing here. I'm making a new class called a whitening filter, and it inherits from filter, that thing I just defined. Okay? The filter thing I just defined, it doesn't really do anything, but it has that method, that filtering data method, right? And that's the point, is that we want filters to have this method where we give it the data and it gives us the new data. And so what I'm going to do is I'm going to give it an init function so that I can create a whitening filter that's a particular kind of whitening filter, right? Then I can instantiate a whitening filter with some parameters, and then I can call that whitening filter with different bits of data as the method, right? Or I can make another whitening filter with different parameters, and then filter other data with that.
Wait, you take data and filter other data with that data and then visual it.
Yes. That's what's weird about a whitening filter, is that the whitening filter, I mean, this is getting into the complicated stuff, but the whitening filter takes some data and figures out how to make white noise out of that data. Then, once it figured out how to make white noise with that data, it can take other data and do the same transformation on it. It's complicated. This is like higher level signal processing stuff, but you don't have to focus on the details. But the point is this. Just look at how I'm using classes here to give you some information or to do something useful. So then this is a bandpass filter. This is a different kind of filter that says filter out all the frequencies that aren't in a particular region that I care about. And in this case, you give it a different input argument. So I'm going to define a different function. I'm going to say, these are the bands that I care about. Now, I can instantiate that with one type of arguments. Like I can do, bandpass filter A equals bandpass filter, and then 10 to 100, right? That's one. Oops. What did I mess up? Oh, I didn't initialize. I didn't do this. Okay.
Oh, that's where I get the new cells from. Thinking cells, I wonder how I match them to create those.
Okay. So you guys see what I did here, right? I have the definition of a bandpass filter. And the bandpass filter takes as an input argument the frequencies that I want to filter around, right? And so then I made two different instances of this class with different input parameters. So these two filters will do different things. So then I can do bandpass filter A some data, right? If data was defined. We can actually, maybe we can do data mpi.a range. Oh, what? No, I did. Numpy. Oh, yeah, no, I didn't. You're right. There we go. So bandpass filter A data. Oh no, sorry. Dot filter data, and then I'm going to give it. Whoa, that didn't work. Oh, yeah, sorry.
What's the frequency anyway?
That example. Well, forget that. That was a sloppy example, but I was trying to make an array for it to sample, but I need to do it better than I'm doing it right now. But the point is that once I have this class defined, or this object which is instantiated from this class, then I can use its method to do something on the data.
What is the sample rate?
The sample rate is, in signal analysis, what it technically is literally the rate at which I sample the data. So remember, I was saying in the interferometer, you've got the little light detector that detects the light coming out of the Michelson interferometer. That we actually, literally, we do this with electronics, but we sample it 16,000 times a second. We say, what's the light level right now? What's the light level right now? And then we record that information into files. And then, so the sample rate in that case would be 16,000 hertz, because we sample 16,000 times a second.
Okay. So what exactly, how exactly does that work in an array?
The array, so right, for a data array, what you have is each element of the array is a sample. And so the sample rate is, what it's saying is, here are all the samples, and here is the time separation between each sample. Because the inverse of the rate is the time difference between each.
I thought what I was thinking was that it was sampling each element of the array 16 times.
No. Right, no. It's saying, it's specific about, so in this example, in this notebook, what we're working with is arrays of data in time, right? It's all, the data is all, is something that's been sampled over and over and over again. In our case, the data is the data from the LIGO interferometer, right? It's the sound that we're recording with the LIGO interferometer. And we record that sound by taking a sample of the light 16,000 times a second.
You know how often that thing's on?
I do.
How often?
It's on right now, and it's on. We basically operate it. We operate it in chunks, so it'll be on for a couple of months, or for like 6 months, and then we turn it off and try to fix it, improve it, and then we turn it back on again. So it kind of goes in a cycle like that. And when we're operating it, we try to keep it on for as long as we possibly can. Yeah, sometimes it goes off because of various technical reasons, but we try to keep it going as much as possible.
Listen to it like live?
We do. We have speakers in the control room.
Wow.
Yeah, so we can listen to it. We usually mostly just look at it on computers, because the computers, even though our ears are very sensitive, the computers are more sensitive. We can do things like, we can listen to that sound sample that I played you earlier, but with the computer, we can plot it, and then we can zoom in. I mean, in fact, that's what we did down here, right? This doesn't have... sorry, this hasn't been run yet. So right. So this up here is all the data this is the data that's stored in a file. And so here is the X is the time array, right? So it's the array of all of the times that the data was sampled. And in the question you were asking about the practice notebook, that's the get detector time array, right? Is this axis. And then this is the get detector noise, basically. And we're doing basically the same thing if you look at that plot, where we have, right? Here is the time array is just the x-axis is like the equivalent of x, and the strain is the same as y. We just named them differently here. And what this is doing is minus tref, is that tref is just this number here, right? So we're taking the time array, and from every element we're just subtracting the same number, and that has the effect of shifting the time down by whatever that number is. So then with the computer, of course, we can now zoom in to like right in the middle, and we can see the structure. We can see structure in here that you can't see very well in here because this just looks like it's solid red. Here we can see the oscillations.
Find a website you can go to get that data.
That what?
The data.
What about it?
Is there a website you can go to or something?
Yes, to get the LIGO data? Yeah, definitely. That's where this notebook came from, that website. I just tried to simplify it, but I didn't simplify it that much.
I just think it'd be really cool to just listen to gravity waves live.
Yeah, you can totally do that. I mean, if you guys, if you're interested, you can go to LOSC.LIGO.org, which is the LIGO Open Science Center. And here you can get Python notebooks that are basically just more sophisticated versions of this capstone. So what I did with this capstone is I took one of these LOSC notebooks and I simplified it, even though I didn't really simplify it that much. I mean, I simplified it quite a bit, but it's still maybe not simplified enough. And anyway, here's a template. That looks like the gravitational wave signal, and then does some plotting of that. And then we made this matched filter search, matched filter class, and then a matched filter object, that's how we look for the signal inside the data. Yeah, white noise filters are kind of complicated. Yes. That's basically the point of it, is that it makes the smaller noises stand out more. That's right.